Hello everyone and welcome back. Now, in the previous video, I introduced you to Lagrange multipliers. And in particular, what we saw in that video is that we now have a way of finding optimum solutions to constrained optimization problems. These constraints can be quite complicated. They could be even nonlinear. But what we really saw is that it all comes down to finding solutions to these Lagrange multiplier equations. Now, what I did in the previous video was all kinds of theoretical examples that sort of illustrate the method. What I would like to do in this video is I'd like to go back to my television example from 2 videos ago, but add in constraints to apply the Lagrange multipliers to it. Okay, so let me remind you that in that example, I was seeking to optimize a profit function. I'll call it capital P. Nothing about the problem is going to change. We're going to use the same profit model, okay? So remember, S is the number of 19-inch TV sets that we produce. T is the number of 21-inch TV sets that we produce. And we had this kind of ugly looking equation, but we could work with it. It's only quadratic in S and T. Minus 0.003 t times s plus 399 minus 0.004 s minus 0.01 t all times t, and then subtracting off the production cost of this thing, it was 40,000, or sorry, it was 400,000 as a base cost. And then plus the production prices of each one of the units. So 225t. Okay, so that's going to be the equation we're going to work with for the rest of the day. Now, we already optimized this thing over S and T being positive. We saw that all it took was finding the gradient and setting the gradient equal to 0. Now what I'd like to do is I'd like to add some constraints. So the first constraint that we have is the obvious one. We obviously need to be producing a positive number of each set, right? It just wouldn't make sense if I told you to produce negative 21 of the 21-inch televisions. So that's a sort of natural constraint here. But let's think about some other ones. Let's imagine that we have a production capacity. So for example, maybe the factory that the company owns has only enough material to produce at most 5,000 of the 19-inch sets and 8,000 of the 21-inch sets. This is a pretty natural assumption, right? Because this tells us that, this is completely dependent on the amount of material that we can get our hands on to build these things. I can't just build infinitely many, right? I need to talk to suppliers, and I need to make sure I can secure the right material to produce these things. Now, on top of that, let's make this a little more interesting, because now this is just a little square in the Cartesian plane. Let's put another piece on this. Let's imagine that our television sets, they have an internal circuit board. It's the same internal circuit board for both television sets, and they come from one company that produces these circuit boards. And in particular, the company says, all right, we can give you circuit boards, but we can give you only 10,000 of those circuit boards per year. That means that no matter how many of each TV that I put together, since they're using the same circuit boards, I can only build a maximum of 10,000 circuit boards, televisions per year of both kinds. So that gives me 5 constraints, S and T being greater than or equal to 0, the production capacity limited by the material for the 19-inch, production capacity limit for the 21-inch, and then this circuit board capacity as well. So this actually defines my feasible region. And so now what I can do is I can look at these things as constraints on my system. Now, what we saw in the previous example with the Lagrange multipliers is the first thing I'm going to need to do is find a gradient of my function p, right? This is the thing that I would like to optimize. Well, in this case, we already computed the gradient 2 videos ago, so maybe you want to recall from there. But it's 144 minus 0.02s minus 0.007t. That's the first component of this gradient. The second component is 174 minus 0.007s minus 0.02t. Okay, nothing too fancy. Remember, just computing these gradients, the first component is the partial derivative with respect to s of my profit function. The second component is the partial derivative with respect to t. Now, what we're going to do is look at these constraints as well. So let's look at the first boundary of the constraint, the most interesting one, right? So the one where things are tied together. So let's define this constraint function, g of s comma t, and let's just call it s plus t. And of course, the constraint is this line. Okay, so what we're going to do is we're going to fix ourselves to that line, and we are going to optimize this function subject to that constraint. Now, the nice thing about this is the gradient is super easy. The gradient, the derivative of this thing with respect to s is 1. The gradient with respect to this, the partial derivative with respect to t is 1. Okay, that's great, right? That makes my life super, super simple, because that tells me that my Lagrange multiplier equation, remember this is gradient of p is equal to lambda times the gradient of g. Well, this thing becomes a nice, simple linear equation. So it's 144 minus 0.02s minus 0.07t. And this is equal to lambda. That's lambda times 1. Similarly, 174 minus 0.007s minus 0.02t. Again, just equal to lambda. And remember the geometric interpretation of these things, right? The gradient of p points in the direction of steepest increase for the function p, right? So if you want to maximize profit, you got to follow that gradient. Now, similarly, the gradient of g runs perpendicular, orthogonal, if we put it in math speak, to the level set given by this constraint right here. So let's put it in a little box so we can really highlight it. Now, the goal here is to find when these things are parallel. That's what the Lagrange multiplier equation is telling us, right? And when these things are parallel, it says the only way you can increase the profit is by moving off of the level curve, right? Because the level curve points in an orthogonal direction. Sorry, the gradient points in an orthogonal direction to the level curve. The only way you can increase p is by moving off of it, okay? So keep that geometric intuition in the back of your mind, just in case you start getting lost in the mathematics of all of this. Okay, now also, we have some more information. We have that we are stuck on this constraint line, which tells us that t is equal to 10,000 minus s. Okay, so what that means is that this can be fed back into my Lagrange multiplier equations. And that originally had 1, 2, 3 unknowns, s, t, and lambda. Now I only have 2 unknowns because I have a way of tying t into s. So that means that you can go ahead and solve this thing, right? Put t into that and solve for s and lambda. Once you have a solution for s and lambda, you get a solution for t as well by putting it into this equation. All right, so I'm going to let you have that fun. I'm going to tell you what the answer is here. In fact, we're going to get s is equal to, let's say it's 50,000 over 13, which in this case is about 3,846. You similarly get t is equal to 80,000 over 13, which is given by 6,154. Notice that these two things do in fact add up to 10,000, which is my constraint. And also, you get that lambda is equal to 24. So you are pointing in exactly the same direction as the gradient of g in this case, because lambda is positive. Remember, keep that geometric intuition in the back of your mind. Now, at these two values, my profit is $532,308. So, the question is, are we done? Well, no, because we need to check all of the other constraints, right? So the only thing that I've done so far is looked at one possible constraint. And we saw that the maximum along that constraint is given by a production capacity of 3,846 of the 19-inch TVs, 6,154 of the 21-inch TVs. Now what we need to do first is check if this is even a maximum over that line, right? Because this is a one-dimensional object. We need to check the endpoints, the same you would do with a single variable optimization problem. So that's what I would like to do next, right? So I can't even move on to the next constraint yet because there's still a few more checks to do. So the endpoints of g of st equal to 10,000. Well, these endpoints, first of all, one of them is given by, let's say, st equal to, so the first one is going to be 5,000 comma 5,000. And where is that coming from? It's meeting this constraint right here. And so since s has to be fixed at 5,000, then t also has to be fixed at 5,000 so that they sum up to 10,000. Similarly, the other endpoint here is when t hits the other extreme, when you have 8,000, so that whenever these things sum to 10,000, so along that line, you are checking this point. Now, you can easily take these numbers and put them into your profit function, and you can show that this profit here, which is on the middle of the line somewhere, right? It's sort of on the interior of the line, returns a larger profit. So these things are not going to maximize the profit. The maximum of the profit along this line, subject to every other constraint, is $532,308. Now, are we done? No, right? So we still have to be careful. Now there are two other main constraints that we need to work with. Technically there are four, although we've checked many of these in the previous example, right? Setting one of st equal to 0. So, four more constraints to check. I will enumerate them here. First of all, s is equal to 0. 2, t is equal to 0. 3, s is equal to 5,000. And 4, t is equal to 8,000, right? So we are fixing ourselves along each one of these constraints, and we are repeating the problem. Now, fortunately, the first two here, like I just said, are relatively easy to handle. You just put s equal to 0 into this equation, and now you've got a single variable optimization problem. You do it over t, and that's going to be for t between 0 and 8,000, right? That's coming from this and this right here. The ones that are going to be a little bit more tricky are s equal to 5,000 and t equal to 8,000. You're going to need to put those values into this equation right here. And then you're going to do another single variable optimization problem. Now again, in all four of these cases, the reason I'm not writing them on the board is because they turn into just standard single variable optimization. The only case that actually requires Lagrange multipliers is the constraint that I've worked out for you here because it's non-trivial. You have s and t working together in a non-trivial way, right? You're not just going along some line that's perpendicular or parallel to the horizontal axis. Now, if I sketch this out for you for a moment, what you can see is that if this is 5,000, if this is 10,000, in this case, you have these endpoints. Sorry, this would be 8,000, pardon me. Sorry, this is the constraint in t. You have one endpoint right here. Let's say this is 5,000, 5,000. And you have another endpoint, which might be somewhere around right here. This is 2,000, 8,000. Then the line that we just optimized over, this is s plus t equal to 10,000. That's what we did all of this work over. The line t is equal to 8,000 is this line right here, from here to here. So that means that s is between 0 and 2,000. It's just this little strip. Same thing, the line s is equal to 5,000, I think I drew this over a little bit too far, is this line right here. So that means that everything in here, including the boundaries, is my feasible region, right? So that's exactly what this is. Everything that's shaded here is a possible value. Now, in the previous example, 2 videos ago, we already figured out when the gradient of p is equal to 0, and we already saw that that takes place outside of the feasible region, right? So it's outside of the production capacities that I have put on this thing. So that means that there's no maximum or minimum inside of this feasible region. It says that all of the action is happening somewhere on the boundaries. And so now what I do is I systematically check each boundary. And you can do that. You can find that the maximum is this one that I've just identified. So it's somewhere around maybe right here on my figure, right? So everything's not drawn to scale, but the point is this is the max. This is the optimum to this problem. All right, like any expert in mathematical modeling, which is what we are becoming through this class, the first thing that we should do once we complete these problems is perform a sensitivity analysis. Now, you can do this on any number of variables that are used throughout this television problem. I want to highlight a very interesting one that you could do this for. For example, you can do this on the constraints. So for example, let's consider the constraint g of s comma t equal to s plus t equal to some constant c. So in this case, c stands for constraint. Now we just did the problem with c equal to 10,000. Now what I would like to know is what is the sensitivity of my solution with respect to this constraint, right? So for example, if the company that's providing me with these circuit boards could maybe produce a couple more of these circuit boards, you know, is this going to help me? Is it going to cost me money? What's going to happen, right? Is it going to be a huge increase in profit, or is it going to be a tiny increase in profit? And this is eventually going to lead to what's called shadow pricing. But before we get there, let's keep working through the same example, okay? So again, we want to solve delta, or nabla p is equal to lambda nabla g. So this is, again, our Lagrange multiplier equation. And in this case, we get the same thing. The only difference is that we have S plus T is equal to C. This tells us that T is equal to C minus S, right? So all of our solutions are going to now depend on C. If you look back at what we did at the beginning of the lecture, C was equal to 10,000. This was an easy linear algebra problem to solve. Same thing here. You can get a solution. In this case, it's going to be 13C minus 30,000 divided by 26. And then T in this case is going to be 13C plus 30,000 divided by 26. And lambda, a little bit of an uglier formula. It's 3 times 106,000 minus 9C. And again, over 2,000 in this case. So all linear functions of C, right? So it's not really that bad. And again, the only thing that I'm doing to arrive at these is I'm taking my gradient of P, which was computed already, setting it equal to lambda times 1, 1, right? That's the gradient of G. The only difference is I have this arbitrary value of C in here, right? I'm just repeating everything I did in the previous section. Now, if C is around 10,000, we would expect that if I vary C, maybe 10,001, 10,010, 9,990, sort of in this neighborhood of 10,000, that the maximum production, the optimal profit, is just going to kind of move around with it, right? So it's going to be tracked by exactly these values of C, T, and lambda. So let's check out the sensitivity of these things. Now, the first thing I want you to note is that the derivative of this with respect to C is just a nice, easy 1/2, 13 over 26. And luckily for me, same thing for the derivative with respect to T. So this is good for me, right? Because this means that I've got a really simple computation right in front of me. I can compute some sensitivities. So sensitivities. Now, let's start with the sensitivity of S with respect to C. And of course, we're going to do this at C is equal to 10,000. That was the one where we computed the answer. We want to know what the sensitivity with respect to this constraint that we computed it to be 10,000 is going to be. Well, in this case, it's going to be the derivative of S with respect to C. That's 1/2 always. And then times the value of C, which is 10,000, divided by that optimal production level at C equal to 10,000. Remember, this was 3,846. And this leaves me with 1.3. Now, let me compute the sensitivity of T with respect to C as well. Again, 1/2, C is 10,000. And in this case, my optimal production was 6,154. In this case here, I've got 0.8. So essentially what this tells me is that these things aren't really all that sensitive, right? A 1% change in C. Remember, a 1% change of 10,000, that's about 10 units, right? So if the company comes back and says, I can actually produce, 10 more than the 10,000 that you were interested in, well, the optimal number that you should be producing is only about 1.3% more of the 19-inch TVs, okay? So again, this is around 30 TVs. Same thing for 6,000 here. We're about 1% more, so about 60 more TVs. So we can do the same thing by computing these derivatives for the price as well. So what I want you to notice is that if I take these optimal production levels and I put them in for the profit equation, so it was the equation that I had across the top of the board at the beginning, well, first of all, before I go ahead and compute this, let's take a look. I can actually use some properties of derivatives to figure out how to do this. This is going to be the partial derivative of p with respect to s times the derivative of s with respect to c. That's a chain rule application. Plus the partial derivative of p with respect to t times the derivative of t with respect to c, plus then the actual partial derivative of p with respect to c. But let's take a look. Let's interrogate this. First of all, p does not depend on c at all, right? C comes in from the constraint, so that is 0. There is no variation in the profit explicitly for when you vary c. This tells you that all of the variation in the profit happens implicitly, right? It happens as a function of s, and it happens as a function of t. Okay, now in this case, you can go ahead and compute all of these things, and I'm going to ruin the surprise. I'm going to tell you that this is equal to 24. Now, most numbers are arbitrary, but this 24 is not completely arbitrary in this case. We've seen this 24 actually come up before. You might have to go back in your notes and remind yourself where the 24 came from, but I will tell you, this was the Lagrange multiplier, right? This was the lambda value. Now, before we keep going deeper on why this is the Lagrange multiplier, let's just proceed for a second, okay? Let's actually just compute some sensitivities like we said we were going to do. So in this case, I've got the sensitivity of the profit with respect to c, and of course I'm going to evaluate this at 10,000, c equal to 10,000. My derivative is 24 in this case, and c value, 10,000, divided by my optimal profit, 532,308. And in this case, we're somewhere around 0.45, right? So my optimal profit is not really that sensitive to changing around these constraints, right? I'm losing out on about half a percentage of profit if you do a 1% change in this constraint C. Okay, so the question is, where did this come from, right? You know, maybe to get that number, you had to do a ton of work, right? You had to take some partial derivatives, put in some numbers, and it was a really big, complicated task. I will ruin the surprise for you. I did not do that. I knew that this was going to be the Lagrange multiplier. Now, how is it that I knew that this thing was going to be the Lagrange multiplier? Well, first of all, we think about that geometric intuition. So first of all, this points in the direction of steepest increase for the profit function P, while the gradient runs perpendicular to the level sets of the function G. Okay, so if this is my function G, so it's just a line, nothing fancy, and in this case it's equal to C, what happens if I change the value of C? All it does is moves upward. So it takes that whole line and moves up like this. And you might get another parallel line. Now notice that that's moving in a perpendicular direction, right? And this is also, from my Lagrange multiplier equation, the same direction that I'm moving in if I want to increase my profit. So what does this actually say? This says, for every 1 unit that I change C, my profit changes by 24 units. That is exactly what this relationship is telling me. And the way that I know that that's true is because if this is the gradient of G, it, from this equation, is 1 over lambda times the gradient of P. Each unit, gradient of G, is moving C. Every time I move by 1 unit in the direction of the gradient of G, that is the same as moving by lambda units in the gradient of p. Okay, so how could this possibly help you? How can this information be used and extrapolated beyond just the mathematics, right? So first thing is, this immediately makes my computations easier. This is something that is always universally true for these problems. You can try and prove it on your own. But this leads to what's called a shadow price in the model. Basically, what this is telling you is that if the microchip or the motherboard, the circuit board company comes back to you and says, we can produce one more unit of these circuit boards, would you like us to do it? Well, what this says is that for every 1 unit changed on the number of circuit boards that can be produced, you gain $24 in profit. Now, that means that if the company comes back and says, I can produce another circuit board for you, would you like me to? Then what I do is I go back to the company, I figure out if it's going to cost me less than $24 to produce another television. If yes, then I'm going to make money on this. If the answer is no, then I don't want to bring in more circuit boards because it's going to end up costing me money. That is the concept of a shadow price. In this case, we have an implicit dependence on the number of units that can be produced maximally, and it tells us how much our profit is going to increase for each 1 unit increase in that production. So again, $24 for every new TV that's produced. That's when I go back into myself and I say, is it going to cost me more than $24 to produce one of these TVs? Because if that's the case, then this is going to cost me money and it's not worth doing. But if it only costs me $23 to produce another TV, then of course I want to say yes to this because I'm making $1 profit. Okay, in the next video we're going to come back and we're going to look at, looking at Newton's method and how it can, again, help us to solve some of these optimization problems in higher dimensions.